So today I will talk about the geometry of the quantum discrete Painlevé equations. So
can you analyze? First, this is not full screen.
Sorry.
When you first tried, it was full screen. Now we see something else. No, it's okay, but
Yes.
maybe
Okay.
you can enlarge it.
Okay. So this is the plan of my talk today. So first I will explain some motivation on the quantization of the isomorphic deformation. And then I will discuss the geometry of the classical continuous discrete Painlevé equations. And in section 3, I will discuss about the quantization of the Painlevé equations, discrete Painlevé equations from the point of view of the fine wide group. And finally, in section 4, I will introduce tau variables and show the main results. Okay. First, I will explain some motivations for the quantization of the isomorphic deformations. So one of the fundamental background on this subject is that the equality of the quantum isomorphic deformation and the conformal field theory. And this relation has been known for a long time. And I will show some well-known examples. First, consider the Schrödinger system, which is given by the n by n matrix Lax form for the vector unknown function. And this is the linear Fuchsian differential equation. And this is the described deformation of this equation. And the compatibility is given by this Rat condition. And this compatibility gives the Schrödinger system. Okay, that is the differential equation for the residue matrices. And it is known that this Schrödinger system is given by the Hamiltonian system, where the Hamiltonian is given in this form, and the Poisson bracket is written in this way. So this is nothing but the Poisson limit of the commutation relation between the matrix unit. So the Dirac quantization of this system gives the Knitznik-Zamoshkov equation. Namely, the Hamiltonian is nothing but Gordon Hamiltonian, and the Schrödinger equation of this quantized system is the Knitznik-Zamoshkov equation. Here, the omega is the second Casimir. So and this relation is known for a long time, and this relation between the conformal field theory and the quantum Painlevé equation is one of the motivation of the quantization. And similar relation is known also for the scalar Lax form. And so consider the Fuchsian equation of the second order of the second order, and this is the deformation equation. And if A is the rational function in Z, then this deformation describes the isomorphic deformation of this second order equation. And the compatibility of the two equations is again given by the Poisson Hamiltonian equation, where the Hamiltonian is given by the function of this guy, and the Poisson structure is given by this this form. And this Poisson structure is the same as that for the KDB hierarchy and known as the Gelfand-Dickey bracket. And of course, this is a classical limit of the Virasoro algebra. So in this way, we also see the classical limit of the Virasoro algebra appear in the isomorphic deformation or the deformation of the second order differential equation. So more precisely, when the potential function is given in this way, this is a function equation of the P1 with n plus 3 regular singular points and additional apparent singularities. And the compatibility of for this function equation is the famous Bilinear system. And when n equal 1 case, which is nothing but the Painlevé equation. And the Hamiltonian function is given by the residue of this term, and which can be determined by the conditions that the point z equal q are the apparent singularity of this equation, and the point infinity is non-singular. And these two conditions determine the Hamiltonian uniquely. And in the conformal field theory, the first condition is says that the point z equal q is correspond to the second level 2 degenerate field, and the second condition gives the SL2 invariance. So the quantization of the n-Bilinear system is given by the Virasoro conformal field theory with n plus 3 primaries and additional level 2 degenerate fields, which correspond to the position z and position qi. So such a relation between such a conformal field theory also related to the gauge theory by the AGT or BPS CFT correspondence. So, and this correspondence also one of the motivation of the quantization of the Painlevé equation. For example, we consider the n by n Schrödinger system over P1 with k regular singular points, and 2 of them are genetic singular points, and the remaining is a minimal, so-called minimal puncture, or the rank 1 matrix. Then the corresponding isomorphic deformation is given is known as the Fuji-Suzuki or Tsuda system, and which is a special case of the Schrödinger system. And when the matrix size is n is 2, then they are the equivalent to the Bilinear system. And this system in the gauge theory side, this system corresponds to the 4-dimensional gauge theory with SUN quiver gauge group and fundamental with 2n fundamental matter and k-4 by fundamentals. And the so-called Kiev formula is known also for this system. So so this is the motivation of the quantization of the isomorphic deformation. So since the isomorphic deformation is a Hamiltonian system, so it is natural to consider their quantization. And moreover, they are related to conformative theory. And also they are related to the gauge and string theories. So the quantization of the isomorphic system is very important. So the aim of this today's talk is to quantize the discrete Painlevé equations. Okay, so let us start. Before consider the quantum Painlevé equation, we record the geometric aspect of the classical Painlevé equations. So there are originally there are 6 or 8 differential Painlevé equations, and they are non-autonomous Hamiltonian systems written in this way. Here, epsilon is a non-autonomous parameter, and when epsilon goes to 0, then the system becomes autonomous, and H and T becomes a constant, and H is become a conserved quantity. So, and the Hamiltonian is given in this way, and except for the most degenerate case of the Painlevé 3, they all are polynomials in P and Q. So in the autonomous case, the Painlevé equation is the conserved system with algebraic integrals given in this expression. And using the Hamiltonians, we can relate the Painlevé equation to the gauge theory. So the correspondence is like this. So here is 8 Painlevé equations, and here is 8 gauge theories, and they correspond. There are one-to-one correspondence between them. Here the SW means the Divergent theory, that is the SU2 gauge theory, 4-dimensional n=2 supersymmetric gauge theory with NF fundamental matters. And AD is the so-called Argyles-Douglas theory, that is a degeneration of the Divergent theory. And one of the easy way to see the correspondence is to compare their geometries. For example, in the Painlevé 6 case, the Hamiltonian can be the level set of the Hamiltonian, that is the solution of this equation, algebraic curve of this equation, and written in the coordinate x and y, which is the q and pq. Then this level set equation can be written in this form. And so we see the factorized structure in top term and the bottom term. And the picture of the curve is like this. So this is the one parameter family of the elliptic curve of by degree 2, 2. And the U is the value of the Hamiltonian. And in the gauge theory, this U corresponds to the so-called Coulomb branch parameter. And we see that we have 8 base points of this family. So here is 4 points, and we have 2 double points here. So double point means we have also the tangential condition on this. So, and for all the classical Painlevé equations, the similar geometry is known, which is first initiated by Okamoto, and they are all 8-point block of P2 or 9-point block of P. Sorry, 8-point block of P1 cross P1 or the 9-point block up of P2. Okay. So, and the similar thing also happened in the discrete case. And for example, this is one of the simplest discrete Painlevé equation, which is a birational mapping on parameter A and variable X and Y. And P is the parameter which increments the P is the non-autonomous parameter which describes the incrementation of the parameter A by discrete time evolution. And when the parameter P is non-zero, then the orbit is like this. But when P goes to 1, then we see that the orbit is on these curves. So so this shows that this mapping is has an integral curve when P is 1, namely in the autonomous case. So in fact, we have the algebraic conserved quantity when P equals 1. And if we consider the complex initial values, then this curve is the Riemann surface of genus 1. And its real projection in the log-log coordinate is given by this picture, which is so-called amoeba. And the previous real slice of the orbit is this corresponds to this inner boundary of this amoeba. And there is another example. This is the famous Jimbo Sakai's QP6, which is given by the birational mapping on the 8 parameter and 2 variables. And the time evolution of this, the time evolution of the parameters is nothing but P shift. And the evolution of the X and Y variables are given by this birational transformation. And again, when the parameter P is equal to 1, then the system is autonomous and we have the conserved quantity. And the explicit form of the conserved quantity is given like this. So here again, we have the factorized structure on the top and the bottom terms. And this is a form of the Hamiltonian correcting the term of in variable y's, and this is the form correcting the variable x. And the top term and bottom term are all factorized. This factorized structure corresponds to this configuration of the points or the position of the tentacles of the amoeba. Okay. So and this curve is known as the 5-dimensional divergent curve, and the parameters H correspond to parameter H corresponds to the tentacles of position of the tentacles of the amoeba, and in the gauge theory sides they correspond to the mass parameter of the gauge theory. Okay. And I have discussed these systems and this guy and this guy. And here is a list of the Sakai's classification of the continuous and discrete Painlevé equations of rank 1, two-dimensional case. And here is the additive case and Q-difference case and the elliptic case. And these three classes correspond to the gauge theory of 4-dimensional and 5-dimensional and 6 dimensions. And only the cases in red letters, they admit the continuous deformation or the differential equation, and other cases admit only the discrete deformation. And all the systems in this Sakai's classification are of genus 1, have the genus 1 conserved curve, and they correspond to the rank 1 gauge theory. So we want to quantize these theories, and in the discrete case, the corresponding conformative theory is not well studied up to now. So we will consider another method, that is a Geomet algebraic method based on the affine wire group. So to quantize the continuous discrete Painlevé equations, we will use the affine wire group approach. And the basic idea is to first we construct a birational representation of affine wire group, and then study a translation T of the wire group as a discrete flow. The merit of this method is, by construction, one can have a huge symmetry, which arises as a commutant of the translation of the affine wire group. And so the main point of this approach is that how to construct the suitable birational representation of affine wire. And there are 3 standard methods known so far. And they are, the first one is based on the Lie theory or Katsumudi theory, and which is defined on some orbit of the some nilpotent orbit of the Katsumudi Lie algebra. And its nice quantization is also known by Gen Kuroki nearly 10 years ago. And so this method is very general, but if we want to apply this theory to E8 case, then the system is very huge. So I don't know how to recover the usual E8 theory from that construction. So the second method to construct the affine wire group is based on the rational surface. That is based on the Cremona isometry of the rational surface. And the E8 case is first considered by Kogo, and that representation was the basis of the construction of the Sakai on the elliptic E8 Painlevé equation. And the third method is to use the cluster algebra, and this method is progress in these days. But today I will consider the quantization of the second method. And so we want to quantize Sakai's approach, and in particular the E8 case, that is the main subject of this talk. So first, let us recall the geometric setup of the Sakai's work. And this is the example of the Jimbo Sakai's Painlevé 6, Q Painlevé 6 case. So we consider the 8-point blow-up of the P1 cross P1 with configuration in this diagram, where the 8 points lie on the 4 lines, 2 vertical lines and 2 horizontal lines. And the Picard group of this surface is generated by the 2 lines, the horizontal lines and vertical lines, and 8 exceptional curves, which appear by blowing up the 8 points. And we also introduce our corresponding parameter H1, H2, and E1 to E8. And these parameters transform covariantly to the basis of the Picard lattice. And these parameters are very convenient to understand the geometric meaning of the representation. The affine value group of this configuration appear as the Cremona isometry, which preserves this configuration. And that is, in this case, such a isometry forms a affine value group of type D15. And this is outer nodes of the linking diagram corresponding to the exchange of these points. And the non-trivial actions are given by the S2 reflection and S3 reflection. They correspond to the exchange of these points. So, and the explicit form of the representation is given in this way. So the S0 is nothing but the exchange of the 2 exceptional divisors. And the S1 is also the exchange of the 2 points. And the S2 is the exchange of the exceptional divisor of the 3rd point and the line, horizontal line, passing through the 7th point. And S3 is also the exchange of the exceptional divisor and horizontal line. So, and the corresponding birational mapping on the variable x and y is given in this form. So the action on the parameter h and ei are nothing but the standard linear reflection on the Picard lattice. Of course, it is written in the multiplicative variable, but essentially they are linear action. Well, more precisely, they are multiplicatively linear action. And the actions on the variable xy are the natural birational rift of this linear action. And the important fact is that this kind of representation, which is known for the classical case, also hold true when x, y are non-commutative variable. That was first observed by Hasegawa-san in 2007. So this birational representation gives the while group representation also for non-commutative case. So, and we want to generalize such a construction for E6, E7, and E8 cases. And the previous example corresponds to this configuration. And in this configuration, we have the curves in green in blue lines, and these curves describe the divisor of the pole divisor of the symplectic form. And in D5 case, the divisor are nothing but the horizontal and vertical lines. So the Poisson bracket is given by standard canonical form in log variables. So, and this is why the quantization is was easy in this case. But in other cases, the Poisson structure is not the standard canonical form. So the quantization is not so easy in these cases. So to overcome this difficulty, we will use another realization of the Sakai surface. So in the that is given in this configuration, in these configurations. So here in E6 case, we consider the by degree 3 and 2 curve. And in E7 case, we consider by degree 4 and 2. And in E8 case, we consider the curve of by degree 6 in X variable and 3 in Y variables. So these curves are of higher degree, but they are still genus 1 because we have many multiple points. For example, here we have double points. We have the double points, and these three are double points, and these guys are triple point. And thanks to these multiple points, these curves are still genus 1, even they are a higher degree. And in this configuration, the pole divisor of the symplectic form is given by the multiple lines. So we have the standard canonical form, and the quantization is given by the usual Q commutator. Okay, so in the we consider the E8 case here, and the first theorem is the following. So let K be the coefficient field, rational function on the parameters, and over the skew field in variable xy with coefficient k, we have the following birational representation of the while group E81. And again, many of the actions are nothing but the exchange of the exceptional divisors, and only non-trivial one is S0 and S3. That corresponds to these nodes. And an important fact is that this transformation gives the wide group representation even for the non-commutative variables. So this is the first result. And to apply this representation to the Painlevé equation, we need to compute the action of the translations. And for E8 case, the translation, there are 120 times 2 directions, including the forward and backward directions. And each of the translations are given by the 58 simple reflections. And they are too big, so it cannot be realized even in the computer. So the problem, how can we understand this translation? And fortunately, in the commutative case, there is a very nice way to understand this action. That is, for any wide group element W, the action on the variable x and y are given in this form, where A, B, and C, and D are some polynomials in x and y. And in general, they are very huge, complicated polynomials, but still we can understand them by geometric term. They can be a very simple geometric characterization. There are very simple geometric characterization of these polynomials. So we can understand the action of the wide group action completely by using these polynomials. And this kind of construct, the fundamental fact of this kind of construction is the lifting of the representation, including the so-called tau variables. So the main problem of our next main problem is to construct such a representation, including tau variables, in non-commutative case. So, in order to understand the quantum wide group action, we introduced the additional variable tau. The tau variables, which is the sigma 1, sigma 2, tau 1, and tau 11. And these variables correspond to the H1, H2, and E1, E2, and E11. And we import the Q commutation relation between these parameters and variables. Here, I.Hj and the Ei.Ej is the intersection pairing of the Picard lattice, or more explicitly, they are given by this inner product. And other cases are commutative. And please note that previously the parameters are central elements before, but in this situation, they are non-commutative with respect to the variable sigma and tau. So the next theorem is that the following. So we have the birational representation of affine while group E81, including the variable sigma and tau. And the action on the sigma and tau is given in this way. Here, the action on the HI, EI, and XY variables are the same as before, so we omit here. So again, the actions S1, S2, and S4, and so on are nothing but the exchange of the points. And only the non-trivial actions are S0 and S3. Okay. And from this expression, if we put X and Y are 0, then we see that the tau variables transformed similarly to the H and E variables. In fact, when we introduce the reduced action on the variable H, E, X, Y, and sigma and tau in this way. So for the H, E parameters, the reduced action is nothing but the original action. And for the X, Y variables, the reduced action is trivial. And for sigma and tau variables, the reduced action is defined by the putting the X and Y 0. So explicitly, the reduced action on the tau and sigma variables is given in this way. And we see this is exactly the same as the action on the E and H variables, or they are exactly the same as the multiplicative linear action on the Picard lattice. So in view of this, this action and this action is the a deformation of the linear action, multiplicative linear action on the E and H variables. And using this R, we have the following realization of the while group action as a joint action. Namely, on the full variables E, H, tau, sigma, and X and Y, the previous while group action can be given by the adjoint action and the reduced action, the multiplicative linear action and the adjoint action. And the adjoint action is a conjugation with the G functions, which is given in this way. Now here, this symbol represents the infinite product or the Q factorial or Q dilogarithm. And in this realization, the break relation for the SI action follows from the Q dilogarithm identity for this Q factorials. And this realization plays important role later. Okay. So the main purpose to introduce the tau variable is the following theorem. So for any while group element W, the action of the W on variable tau is given in this simple form. Here, the this part is a monomial part of the sigma and tau variables. And here is a function in x and y variables. A priori, they are rational function in x, y, but they are in fact a non-commutative polynomial in x and y. So this representation has remarkable holomorphic or regularity property. And this regularity corresponds to the so-called Laurent phenomena in the cluster algebra, or the singularity confinement phenomena in the Painlevé equation, discrete Painlevé equation. And when q equals 1 case, these polynomial can be determined by its degree and the multiplicity data at the point pk. And we want to formulate the analogous characterization of these polynomials in quantum case. First, here is our example of the F polynomials. So consider this sequence of simple reflections, and the action on the E variable is nothing but a multiplicative linear action, and they are given in this way. And the action on the tau variable, the monomial part is essentially the same as this guy. And we have extra factor f, that is our non-trivial function in x and y. And they are a priori a rational function in x and y, but we see that they are in fact the polynomials. In this case, they are by degree 2 polynomial. So degree 2 in x variables and degree 2 in y variables. And moreover, we see the factorized structure on the lowest term and the highest term in y variables, and also in the lowest term in x and the highest term in x, also the factorized. So, and this factorized structure shows the vanishing multiplicity on each point in the point configurations. For example, the zero multiplicity at the point E1 is 1, and E2 multiplicity on point P2 is 1, and the multiplicity on point that on 10th point, the multiplicity is 2. And this multiplicity can be lead off from the exponent of this monomial factor. And also the degree by degree can be also seen from this monomial parts. So, and this is the general structure of the polynomial f. So we define such polynomial in this, we can define such polynomial in this way. So for given degree and multiplicity data d and m, we define q difference operator, or the q non-commutative polynomial f by the following two expressions. So in correcting the term x, then we have this kind of factorized coefficients. And when correcting the term in variable y, then the coefficient also have this factorized property. And these two conditions determine the all remaining coefficient uniquely up to constant normalization. So, and these remaining polynomials are some polynomial in y and polynomial in x, whose degrees are fixed by the each term of this guy has a correct degree assigned by this d parameter. And these two conditions determine the non-commutative polynomial f uniquely. And in view of the Q difference operator, this condition and this condition shows that this Q difference operator has the non-logarithmic singularity around x equals 0 and x equals infinity. Or this second expression shows that this difference operator has the similar non-logarithmic singularity around y equals 0 and y equals infinity. And here, in the first expression, we in this picture, we are considering the F polynomial as a difference operator with respect to variable x, or the difference operator with respect to the variable y. In the first case, we consider the y variable is the shift operator on x. And in the second picture, we are considering the x is the shift operator on the y variables. And this condition shows that in both picture, they have the non-logarithmic singularity on x equals 0 or infinity and y equals 0 infinity. So non-logarithmic means that these multiple zeros shows the resonance of the exponent. And if we have the resonance of the exponent, there may appear logarithmic solutions in general. But in this case, even though the exponents are resonance, but all the solutions are still regular. That is a non-logarithmic property. And this non-logarithmic property is the most important characteristic property of this polynomial, non-commutative polynomial. So this is the main theorem. For the orbit of the EI, we can read off the degree and the multiplicity by the multiplicative linear action. And then from these data, one can define the polynomials according to the previous definition. And the main theorem says that this polynomial is exactly the same as the polynomial appearing in the while group action on tau variables. And this is a geometric characterization of the so-called tau quotient of the while group action. And moreover, from this polynomial, one can recover the birational action on the x and y variable also, because the action on x variable and the y variable can be written by the ratio of the tau variables. So this polynomial essentially determines all the while loop action for any W. And the key fact of this theorem is the non-logarithmic property of the F variables. And this property comes from the realization of the while group actions by the adjoint action. And for the detail, so please see the paper, the Moriyama-san and myself. Okay. Okay. So finally, I will comment on the bilinear realization of the quantum Painlevé equation of type E8. So consider this seed equation. Here is 4 3-term relation, bilinear 3-term relations, and 5 and 2 constraint equations. And by taking the infinite many copy of these equations by while group actions, we have the infinite system of the bilinear relation on the tau function on E8 lattice. And the theorem is that this over-determined system for the infinitely many tau variables is consistent, and the solution is given by our F polynomials. So this infinite system of bilinear relation gives the bilinear form of the quantum Painlevé equation. Now, there is also the application to the quantum curve, quantum Divergent curve, but so I have 1 minute. So sorry. So when the parameters are generic, then the curve passing through these multiple points is given by this trivial form. That is nothing but multiple lines given in blue lines. But when the parameters are special, that means this combination is equal to 1, then the curve passing through these points is given by 1 parameter pencil. And this pencil is nothing but the algebraic integral of the autonomous quantum Painlevé equations. And the explicit form of the curve is given in this way. And this is originally obtained by Moriyama-san as a quantum Divergent curve. So this curve corresponds to the conserved quantity of the quantum E8 Painlevé equation in autonomous case. So, and this conserved quantity should be correspond to the trigonometric Rice-Fandi operator of type E8. In the classical case, this correspondence is known by the work of Takemura and known Rice and myself. But in this realization, in the quantum realization, it is not known. And there is a nice application of the isomorphic deformation to quantum spectral theory by Bernstein and Gabriel and Grass. So I expect that this kind of formulation can be also useful for the discrete case for this quantum operators. So let us summarize the talk. So I have reviewed the quantum Painlevé equation in view of the geometry and the gauge theory. And I constructed the quantum birational representation and its lift, including tau variables. And the main result is the regularity of the representation. And I also showed the bilinear form, and I gave the conserved quantity in the autonomous case. That is all. So thank you very much.
Thank you very much for your talk. Please, questions.
I have a question.
Excuse me, please.
So, okay.
Okay.
Okay. So thank you. From the look of the various relations you showed on how your Weil reflections were acting in this birational way, it feels very much like cluster algebra is underlying this. So now that you understand very well all these actions, can you come up with a cluster algebra description?
And it is quite naturally expected. And but I'm not so familiar in the cluster algebra. So, but some people say that the same structure also appear in the cluster theory. So, in the cluster theory, there is also the this kind of the reduced action and the full action. And the reduced action is essentially the linear action. And such linear action determines all the structure, and the full representation, it can be recovered from this kind of the reduced linear action. So and it is said that such a structure is a general structure of the cluster algebra. So I think this construction is also the one of the example of the cluster theory. So, and if we can understand in such a way, we can understand more general case or higher genus or elliptic and so on. So it is very important problem, I think. Thank you.
I have a technical question. You have you spoke about 120 times 2 directions, etc.
Yes,
so
yes.
I'm a little bit confused where this comes from, because a affine group is just extension of root lattice by the finite group. So
Yes.
you have apparently 8 directions and not so many of them.
Yes, yes. The lattice is 8 dimension. So the independent direction is, there are only 8 independent directions. And other 120 are the combination of them. For example, in the 8th lattice, they are 2 dimension, but they are triangular lattice. So we have 6 direction with 160 open and 60 degrees. So we have 6 directions of the translations on 2-dimensional space. Okay. So in the 8-dimensional lattice, we have 120 directions. Of course, only 8 is of them are linear independent.
That's, I see.
And all the directions are equivalent in this case. Okay. But but the other directions, they are different. So, and they are linearly dependent, but we can consider 120 directions simultaneous. They are commuting with each other.
So maybe you could say that this direction corresponds to E8 roots.
Yes. Yes. And the minimal translation in the E8 case is the rootless. So,
Mhm.
okay.
Maybe there are more questions.
Well, maybe just a comment to Philip's question. And as our speaker said, that the construction with clusters is expected, and actually it's, well, it's almost known. Yeah. Maybe not to such deep, detailized end as we just heard in this talk, but clearly this is related with the autonomization of cluster integrable systems. So Philip, so your expectation is absolutely
Okay. Okay. Thank you.
And well, maybe it's already not time for the questions. I wanted to ask about this formula. The bracket x with y is equal to xy times xy minus 1. So that was for E6, yeah. And what are the analogs of E7 and E8 of this lowest line?
Excuse me? So,
What are analogous formulas for E7 and E8?
So in the E7 case, and so the configuration is given in this way. So for example, in this case, the exchange of these 4 points and exchange of these points correspond to the 4 nodes on the linking diagram, and the exchange of this guy and the exchange of this guy correspond to the top node and middle node of the E7 linking diagram. So the non-trivial, only these 2 exchanges are non-trivial. And similar thing is also in this case. So we have exchange of these guys, and the exchange of these 2. And the non-trivial action is the exchange of this one and this one, and exchange of this one and this one. So, and these actions are essentially the same to the exchange of this one and this one, and exchange of this one and this one. So the actions are essentially, in all cases, the actions are essentially given by this one and this one. And other wide reflection is nothing but the exchange of the parameters. So in all the cases, the actions are essentially given by this transformation.
I think Andre's question was regarding the Poisson brackets of X and Y.
Yes, yes.
This one?
Yeah. How does it generalize?
The right-hand side of the Poisson bracket of X with Y.
Excuse me?
ポワソンブラケット E7、E8 の時にどうなるんですかっていう質問。
Sorry. So in the E8 case, we have a nodal curve, and the pole divisor is the zero locus of this pole divisor. So the denominator is non-trivial polynomial in this case.
I see the origin. Okay.
I suggest to stop with questions.
We should thank the speaker for wonderful talk.
Yes, and